All right, good morning, lads and ladies. Welcome back to our last class before spring break. Also our last class before exam 2. So this is our exam 2 review. I've been looking at the Discord and there's one problem there that I would like to address here as a part of our review. But aside from that, the rest of the class is yours. So let me waste none of your time. We'll come in here and get started right away. Please dump into the chat any problem numbers you would like to see worked. So, if you want to see homework 6, problem 5, just type homework 6, problem 5 into the chat. And I will move through those as efficiently as I can and try to do as many as possible. So homework's here. We can pull up any one of them that we want. The one problem that I saw requested in chat, unfortunately, I don't see my, oh, Mackenzie's here. Okay, yeah, so Mackenzie, the problem you were asking about in the Discord, we can begin with that one. Oh, wait, that's not the good pen. Where's the good pen? We want to find the limit as x goes to infinity in 1 plus a over x, all raised to the power of bx. Oh, this is also not a good pen. Damn. All right, we'll try this. So I want to find the limit. Yeah, this one works. As x goes to infinity of this expression. This is a hard problem. I'm going to say it at the start. The reason I'm showing you this and putting this in this homework set, and Hamlet, come here, bub. The reason I'm showing you this problem now is because it's something I want you to remember forever. It's a tricky problem, but remembering the result here is something that will help you out, not just in Calc 1, but also in Calc 2. Here's what we're going to do. If we just plug in, right, if we just start plugging in, this looks like 1 plus a over infinity raised to the b times infinity. A over infinity here for any constant a is 0. So this is like 1 plus 0 raised to the power. Similarly, b times infinity for any constant b, that's going to be infinity. So this looks like 1 to the infinity, which is an indeterminate power. And the way you handle these is we're going to say let f of x be the function 1 plus a over x raised to the power of bx, like this. Then the natural log of f of x, we'll take the natural log. Our goal, remember the goal with indeterminate powers, we want to change these into indeterminate ratios, something like 0 over 0 or infinity over infinity, so that we can apply L'Hopital's rule. And that's why we're taking the natural log. It's going to help us do that. So first, just shoving this inside of the ln, we get that. But then applying the rules for the natural log, that power can come out front like this. So this is just one of the many reasons why back in all those early algebra classes, we really harped on you guys to learn the algebra properties of the logarithm. It's a very useful tool. If I try to take the limit of this expression as x goes to infinity, the inside of the log is 1 plus a over x. That's the piece that went to 1. And out here, this piece goes to infinity. So we would say now lim x to infinity of the natural log of my function. This is the limit as x goes to infinity of bx times the natural log of 1 plus a over x. This piece b times x is still going to infinity. And this piece, 1 plus a over x, is still going to 1. So this is infinity times the natural log of 1. But the natural log of 1 is 0. So this is infinity times 0. And that's an indeterminate product. Okay. Come on, pens. So we've gone from an indeterminate power, 1 to the infinity, to an indeterminate product, infinity times 0. And the next step from here is just going to be to do a little bit more algebra. So I'm going to take this expression, I'm going to come back and rework it from here. This is equal to lim x to infinity natural log of 1 plus a over x divided by 1 over b times x. So this bx, I can shove that downstairs as 1 over bx. And I'm doing that because this is the piece that goes to infinity right now. So if I do this, if I flip it over and shove it downstairs, that piece is now going to go to 0. And upstairs, I still have a piece going to the natural log of 1. So now this looks like 0 over 0. So I can apply L'Hopital's rule. This is an indeterminate ratio. And those are the things I'm allowed to use L'Hopital's rule on. So now I use L'Hopital's rule. I get lim x to infinity. We need to differentiate the top and differentiate the bottom. The derivative of ln of 1 plus a over x is going to be 1 over 1 plus a over x times the derivative of 1 plus a over x. Remember, that's how natural log derivatives work. It's 1 over the inside times the derivative of the inside. It's the chain rule. And downstairs, 1 over b times x, I need to differentiate that. That can be thought of as a quotient rule thing, or if you're clever, you can think of it as a power rule and a chain rule thing. That's bx to the negative 1. So that's going to be negative 1 over b times x squared. Upstairs, I still need to take the derivative here to finish up my chain rule. So I'll have 1 over 1 plus a over x times the derivative of 1 is 0. The derivative of a over x is negative a over x squared. So I have that all divided by negative 1 over b times x squared. And it might not look like it's getting better, but at this stage, if we do some algebra, things will get much, much nicer. This is lim x to infinity. 1 over 1 plus a over x, that's this piece, times negative a over x squared times, now I can bring this piece back upstairs because the x squared here is going to cancel with the x squared here. This is negative bx squared over 1. And we can cancel the x squareds. Oh, is this guy working? Okay, and so now I have negative a times negative b, which is going to be positive a times b over this 1 plus a over x. So I'm going to pause here for a second. I want you guys write anything you need to write and ask any questions you have about what we've done so far. I see there's something in chat. Let's address that. Where did the 1 over bx squared come from? That's the derivative of 1 over bx. So if we want to see the derivative calculations that I'm doing here, one over bx all primed. This is 1 over b times 1 over x all primed. 1 over b is a constant, so this is 1 over b times 1 over x primed. And if you prime 1 over x, you get negative 1 over x squared. So if you put that together, that's negative 1 over bx squared. That's that derivative.
How did you determine that b was like a constant and x wasn't? Because they're just both letters.
Well, the limit says lim as x goes to infinity.
Oh.
Right? So x is our variable just by virtue of that. But also, if you look at the statement of the problem itself, I think it'll say prove for any constants a and b, da 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 da. Where was this guy? Oh, is he up here further? He is, yeah. He's one of the last L'Hopital's rule problems, right? Yeah, right here. Oh, no, they don't say it explicitly. Okay, so then the limit just has an x here, right? So we're thinking of x as the variable. That's kind of our clue that a and b are constants. Yeah, fair question, especially since the problem doesn't say it. If I was to write this problem out, I would say prove that for any constants a and b, blah, blah, blah. Other questions so far?
Yeah, why did you initially start out by taking the natural log?
So anytime you encounter an indeterminate power, 0 to the 0, 1 to the infinity, infinity to the 0, anytime you bump into those things, indeterminate powers, the game is to take the natural log, because that will let you turn your indeterminate power into an indeterminate product. So as soon as I recognized this as an indeterminate power, I knew I needed to take natural logs.
So an indeterminate power is either 1 to infinity or 1 to 0. Is that correct?
1 to the 0 is not an indeterminate power, but 1 to the infinity is, 0 to the 0 is, and there's one other. I think it's 0 to the infinity. Let me take a look here. So indeterminate powers. 0 to the 0, yeah, infinity to the 0, and 1 to the infinity. These are our indeterminate powers.
All right.
So anytime we bump into one of these, the game is to take natural logs. There's another way to do this, but I think that this is a little bit more complicated. So this is the way I would recommend you think about it. If you want to see an alternate approach, slightly more complicated, you can read this section of the textbook.
Okay. Appreciate it.
Yeah, of course. Other questions so far in this problem? So we take natural logs, that turns the indeterminate power into an indeterminate product. And then we play this sneaky algebra game where we take one of the pieces and shove it downstairs as its reciprocal. That'll turn the indeterminate product into an indeterminate ratio. Once I have an indeterminate ratio, I can apply L'Hopital's rule. I take my derivatives very carefully, simplify the algebra, and that gets me here. And the good news is that here, down at this very bottom line, if I plug in infinity for x, this will be a times b over 1 plus 0, right? A over infinity as x goes to infinity, a over x goes to 0. So this is just a times b, right? A times b over 1, which is a times b. So what we've seen is that the natural log of my function goes to a times b. Back up just a little bit. since the natural log of my function has limit a times b, remember the definition of natural log. The definition of the ln says that if the natural log of y is equal to, I'll use a letter we're not using here, w, that's the same thing as saying that y is equal to e to the w. So if the natural log of my function goes to ab, if the limit as x goes to infinity of the natural log of f of x is equal to a times b, this means that the limit of f of x itself is going to be e to the ab. See what I'm doing here? Kind of to undo the log, this thing goes in the exponent. So to undo this log, this thing goes in the exponent. There's some weirdness with the limit here, right? Like this isn't a purely algebra statement, and technically there's a little bit more going on, but this is the easiest way to think of it. If the ln of your function goes to some constant, then the function itself goes to e to that constant. If you really want to be careful about this step, I can show you the details behind this, or if you're comfortable accepting it as it is, we can accept it as it is. Would we like to see the details here? All right. So remember, we have this theorem. It's actually the definition of continuity. The limit as x goes to a of f of g of x, this is going to be the same as f of the limit as x goes to a of g of x for any continuous function f. So according to this theorem, I can kind of play around with the limit over here. Therefore, if the limit as x goes to infinity of the natural log of f of x, that's equal to a times b, I can shove the limit inside the log. This is equivalent to saying the ln of the limit as x goes to infinity of f of x is equal to a times b. And now I can apply the definition. Now I'm at a place where I've got the ln of some shit equals some number, the ln of some shit equals some number. So you can undo the ln using the definition of the ln, and you get lim x to infinity f of x equals e to the ab. I would not require you guys to show these details. I would want to see all the work up to here, right? Up to here. And then you could just say, okay, since the limit of my function goes to ab, the limit, the limit of the log of my function goes to ab, the limit of my function itself goes to e to the ab. I would be okay with you guys getting to here and then just saying this. I'll put the stuff that you could omit in brackets. So a kind of minimal good solution is all the non-bracketed stuff here, right? You do everything that we did to get up to the a times b, and then you just say, okay, the natural log of my function has limit ab, which means the function itself has limit e to the ab. So the details here are kind of neat. Yeah, so let me kind of go back through the highlights here, right? Let's do that. I'll do the uncovering method. So we'll pretend like we're giving a talk at a math conference in the 1990s. That's a good question, Joe. It's actually up to us. So Joe asked, how do I know which piece to send downstairs to make the ratio? I could have sent the natural log piece downstairs. I imagine which one would I rather differentiate? Would I rather differentiate 1 over bx or 1 over the natural log of 1 plus a over x? One of those is harder. I choose to do the easy one because I'm lazy. But it would work out same either way. You just have more work, more chain rule to do if you did it the other way. So at the start, I go, okay, well, let's just plug in infinity and see what I get. Oh shit, it looks like 1 to the infinity. Damn, I don't know what that is. That's an indeterminate power. So I know what to do with indeterminate powers. I take the log. So I'm gonna say, okay, this is my function. This is the thing I'm trying to take the limit of. So I'll go ahead and just call that f of x. And then because I got an indeterminate power, I know to take the natural log. So I say, okay, f of x is this, which means that the natural log of f of x is this. Now I use rules for logarithms to bring this bx from inside the log as a power to down front the log as a multiple. And I go, okay, this is looking better. If I try to take limits of that, so I just take a limit everywhere in the line above, the limit of the natural log of f of x will be equal to the limit of this thing, because the natural log of f of x is this thing. So I just take limits everywhere. And now this piece, bx, still going to infinity like it did before, but it's not in the power anymore, it's down front. And inside the logarithm, I have 1 plus a over x, just like that went to 1 before, it's going to 1 now, but it's inside the logarithm. So I have infinity times the natural log of 1, which is infinity times 0, because the natural log of 1 is 0. I go, oh shit, that's still not good. That's an indeterminate product. But indeterminate products are easier than indeterminate powers. So at this step, even though I might feel a little bit discouraged, I realize I'm going in the right direction. Things are getting better. The way we handle an indeterminate product is by picking one of these two pieces, either the infinity piece or the 0 piece, and shoving it downstairs as its reciprocal. And Joe asked a really good question. How did I choose, like, which piece needs to go downstairs, the bx or the natural log of 1 plus a over x? I could have shoved this downstairs, and that would have given me bx divided by 1 over the natural log of 1 plus a over x. But that's harder to differentiate. So I know I'm going to have to differentiate the top and the bottom. My goal is to get to an indeterminate ratio and use L'Hopital's rule. So I take the simplest piece and I shove that downstairs as its reciprocal. Then when I take limits, I notice that the top is going to 0, the bottom is going to 0. Yay, it's an indeterminate ratio. That means I can use L'Hopital's rule. So in my next step, I apply L'Hopital's rule. L'Hopital's rule says take the derivative of the top, which is this. The derivative of the natural log of some shit is always 1 over that shit times the derivative of that shit. And the derivative of the bottom, the derivative of 1 over bx, that's the derivative I calculated on the side here. That's not hard. That's negative 1 over bx squared. I finished my chain rule work upstairs. So that gets me this. And I recognize that I've got like a something over x squared upstairs, a something over x squared downstairs. So I know there's going to be some cancellation. So I move forwards to do some algebra. Indeed, when I flip this piece upstairs as its reciprocal, I just bring this back up. He's going to be negative bx squared over 1, which the x squareds can cancel with the negative a over x squared term. This piece just chilling. When the x squareds cancel, this piece becomes negative a, this piece becomes negative b. Negative a times negative b is positive ab. Fabrice asks about the denominator here. So as x goes to infinity, bx gets bigger and bigger and bigger and bigger. 1 divided by infinity is 0. So 1 over bx, that really does go to 0 because bx goes to infinity. Remember, the limit here is as x goes to infinity. From there, I have negative a times negative b, which is positive ab, and I still have this piece. So this piece times positive ab is just ab over 1 plus a over x. Now, as I send x to infinity, that a over x goes to 0. So I just get ab over 1, which is ab. And that brings us to the step we were talking about. So the limit of the natural log of my function is a times b. That means that the limit of my function itself, since the limit of the natural log of my function is ab, I know that the limit of my function is e to the ab, because that's how you undo the log. You exponentiate. And then the details behind that exponentiation are all here. So Joe, are we asking about the step from here to here?
Yes, sir.
Okay.
And then the one after that, the one line after that too.
Okay. So let me come back here and just pay attention to the algebra. I've got a big fraction. Here I've got 1 over 1 plus a over x. Here I've got negative a over x squared, and downstairs I have negative 1 over bx squared. I want to divide this whole numerator by this fraction, right? So how do you divide by a fraction? You flip and multiply. So this is 1 over 1 plus a over x times negative a over x squared times bx squared, negative bx squared over 1. All right, so this guy comes upstairs, flip and multiply. Now that's 1 over 1 plus a over x times, let's combine these into a single fraction. We'll have abx squared over x squared. All right, if I multiply these two fractions, I just forget about this guy for a minute. I'm just going to multiply these two fractions. You multiply fractions straight across. So negative a times negative bx squared is positive abx squared. And downstairs, x squared times 1 is just x squared. So now I can cancel the x squareds. I'm still ignoring this first part. When you cancel those x squareds, you get ab over 1. And now if I multiply these two fractions straight across, I get ab times 1 over 1 plus a over x times 1. So that's how we simplify those fractions. So then the limit of this is equal to the limit of this. And the limit of this is ab over 1, or just ab.
So, all right, so I'm sorry, I don't mean to keep making you go back up top, but could you just kind of go over how you get the 1 over bx to negative 1 over bx squared again?
Yeah, it's right here.
So you take the derivative of 1 over x. I'm still a little fuzzy on how you get the x squared downstairs.
Well, what is the derivative of 1 over x? Easiest way to do this is to think of it as x to the negative 1. So 1 over x is x to the negative 1. And if I want to prime that, I get negative 1 x to the negative 2 by the power rule.
Mhm.
which is -1 times 1 over x squared, which is -1 over x squared. And then the b downstairs is a 1 over b constant multiple that can pop out of the derivative, and then I just bring it back in like this.
So, all right, so you're doing the same thing for the 1 plus a over x?
Yep,
Yeah.
and same sort of thing for 1 plus a over x. Sorry, this work is kind of getting all over the place now, but yep, same sort of business for that. If I want to prime 1 plus a over x, the 1 differentiates to 0. So this is the same as 0 plus a over x primed, which is the same as a times 1 over x primed. And the derivative of 1 over x we just saw is -1 over x squared. So this is a times -1 over x squared, which is -a over x squared. Yeah, so there's lots of little things here. This is kind of the thing about chapter 4 is that we take all that stuff we did back in chapters 2 and 3 and kind of build new shit out of it. So all those little things from chapters 2 and 3 need to be like quick and smooth for the stuff to feel good. So think of this as kind of stretching those differentiation legs. You learned how to do it before exam 1. Now we need to get really good at it.
Appreciate it.
Of course. Any other questions on this problem? All righty. So what else do we want to see? This is your guys' day. What else would we like to practice here on your review day?
So
I don't have a specific like number, but some more 4.7.
Okay, yeah, some more applied optimization. Robert, what were
Yeah.
you gonna say?
well, I don't mean to go way back in the homeworks, but in homework 7, I was a little confused on number 12. It's about the absolute maxes and mins stuff.
Okay, no, yeah, let's take a look at one of those and then I'll do an applied optimization problem.
Okay.
All right, so we want to find the absolute max, absolute min, local max, local mins for f of x equals sine x on the interval of 0 to pi over 2. Is this the one?
Yeah, so I was a little confused because whenever I did the maximum, it accepted a DNE where it's clearly, when you look at the graph like on Desmos, it's 1. And I was very confused as to why it was a DNE.
It has to do with the domain restriction here. You see how they're restricting the domain?
Yeah,
0 is less than or equal to x is strictly less than pi over 2.
yeah.
So the sine function is a function we should know well. Let's graph that.
So wait, hold on. Is that less than or equal to, or is that just less than?
One of them is less than or equal to, the other one is strictly less than, and that's why you don't have an absolute max.
Okay, that's why I didn't.
So just for fun, since we're here, let's go ahead and finish it. I'm going to draw the full sine function because I didn't know this guy. I'll mark this as 1. I'll mark this as -1. I'll mark this as 2 pi. So here would be pi, and right over here would be pi over 2. We know that this guy, oh, sorry, that's cosine. We know this guy starts at 0, 1, back to here. So the sine function looks like this, and if we weren't restricting the domain, you would be 100% right to say that there's a local and absolute max here.
Mhm.
And a local and absolute min here. But if we restrict to the left closed right open interval 0 to pi over 2, then this guy is filled in, but this guy up here is open. So kind of here is what that function looks like when I restrict it to that interval. So here I don't actually hit the local max, right? I don't attain any max. So there's no maxes. And the abs min is 0 attained at x equals 0. And if you remember, I talked about this a little bit. Desmos doesn't acknowledge endpoints as local extrema. So it's going to say there's no local min, although technically this would satisfy the definition of a local min.
I think because whenever I drew it out, I didn't notice it wasn't an equal to.
Yeah, that would make this, that would certainly change things. Yep.
So I looked it up on Desmos and I'm like, okay, where am I going wrong here?
One of the downsides to Desmos is really good. And it's almost like its goodness hurts us here. So the difference between that function with the closed endpoint and the open endpoint is just at the endpoint, and you really can't see it, right? Because one point is infinitely narrow. But if we turn this off and we come over here and zoom in with it like that, it should give us, oh no, even there, it's not going to do it. Yeah. So we really can't see the difference. I guess that gray dot is kind of the difference, but it's frustrating how little a difference there is. It would not be obvious, I agree, just from that. But drawing these by hand, and this is something I'm really glad we're talking about this actually, because in these homeworks, it's really crucial that you draw the graphs by hand. Using a graphing utility, if you're stuck, is fine. It is, it absolutely is. But before you try to answer the question, make sure you draw the graphs by hand, and kind of between looking at the graphing utility and drawing the graph by hand, reread the problem to make sure you're not missing any details. All right, where do we want to go from here? I saw a bunch of other stuff come up in chat. I think Mackenzie wanted to see an applied optimization problem, and then I'll turn to the questions that have been added to chat since then. Which applied optimization problems did we see? We did the oil can and the fence, right? So there's another good one here. I did this one with my honors class the other day, and I made so many mistakes as I did it. It was terribly embarrassing. But it's a good problem, and I won't make so many mistakes with you guys, I promise. So it's the open box, this one, 15. So I've got 1200. An engineer, this is an applied optimization problem. An engineer wants to design a box with a square base and an open top using 1200 square centimeters of material. What is the maximum volume of such a box? So the idea here is that you've got you're making a box. I'm going to do my best to draw this in 3D. You're making a box. And the base has to be a square. Base isn't allowed to be like any rectangle, has to be a square, which means that this dimension is the same as this dimension. All right, all of these are x. And then the height can be whatever the hell you want. All about the same length. These are a little shorter. Okay. It's a little short too. Okay. All right, that's about as good as I can draw that. So the height is allowed to be some other thing, but the base has to be square, which means the side length here and the side length here have to be the same. The top is open, so I'm not worrying about anything related to the top. Okay, the thing I want to maximize is the volume. And the equation for the volume of something like this, remember for any sort of box, it's like length times width times height. So this is x times y, which is just the same as saying v is equal to x squared times y. What is my constraint?
What do you mean by constraint?
You guys remember the farmer fence problem with the river?
Mm-hmm.
The fact that we only had 2,400 feet of fencing to work with there meant that the perimeter was equal to 2,400. That was our constraint. Or the oil can problem, the can had to hold 1 liter of oil. So the volume being equal to 1 liter, that was our constraint. So there's always two things. There's always the thing you're trying to maximize or minimize, and then there's the other bit of information that you need to keep in mind. That other bit of information is called the constraint.
Okay, so it's the 1200.
Mm-hmm. What has to be equal to 1200?
Volume.
I'm sorry, go ahead.
Oh, sorry, volume.
That's not the volume. The volume is the thing I'm trying to maximize.
The area?
Yeah, the surface area. Right, because that's how much material I have to make this box. So if we come in here and start trying to calculate the surface area, what is that?
For y and x or plus x?
So let's do the sides separate from the base, right? Each of the sides here, this guy has area x times y, right? Because if you just look at him, he's a rectangle whose width is x and whose height is y. And there's 1, 2, 3, 4 of those, right? Each one of these sides, 3, 4, has width x and height y, width x and height y, width x and height y, width x and height y. So the surface area from the sides is 4xy. And the surface area of the base, what's that?
X squared.
Yeah, good, x squared. And because the box has an open top, there's no surface area for the top, right? We don't need to worry about that at all. So my total surface area, I'll call it S, is equal to x squared plus 4xy. And I know that this has to be 1200. So my constraint is 1200 equals x squared plus 4xy. Is everybody with me so far? Let's say make sure you get this in your notes nice and organized, because this is the setup for the problem. And think about what we did. We started by drawing a picture. Then I labeled each of the side lengths, making sure to pay attention to the fact that the base was square. Since the base was square, these each had to be x. But since the height is allowed to be whatever you want, I used a different variable there. Then I reread the problem and I say, what are we trying to do? Well, we're trying to find the max volume. So the thing I want to maximize, I just write down the thing I want to maximize is volume. And then I find the equation for the volume. That's always length times width times height for a box. So that's x squared times y. The constraint, the thing that limits me, right? If I want to build the biggest box I can possibly build, if you don't give me like some constraint, if you don't tell me, hey, you've only got 1200 and whatever, then I can just build a fucking huge box, right? There's nothing to limit the size of the box without this extra bit of information. So this extra bit of information saying I only have 1200 square centimeters of material to work with tells me that, well, okay, as I'm building my box, I can't have the surface area be greater than 1200. So then to come up with the surface area, I think about the surface area of the base, and this is Fabrice's question. I think about the surface area of the base plus the surface area of the sides. Each one of these sides, if I look just at this side here, just at this side, his surface area is x times y. And how many of those do I have? Well, I have this one, but then I also have this one, and this one. So there's 4 sides, right? Picture a box, hold one in front of you if you must. There's 4 sides. Each of those sides has the area x times y. So that's the 4xy. So the base has surface area x squared, and each of the sides has surface area xy. There are 4 sides and 1 base. So we add 4xy, that's the surface area for all the sides, together with the surface area for the base, which is x squared. Does that help, Fabrice? Cool. All right. What do I do from here? Who remembers how we do these?
You
Set
solve for
one equal to like either x or y.
Yeah, I got to solve this for either x or for y. Now, since this has both an x squared and an x, it's going to be easier to solve for y. All right, the y just appears here and only in one place. So I can solve this for y. Let's solve the constraint for y. That's correct, Luke. Yeah, if the top wasn't open, we would have 2x squared plus 4xy. So if I solve this apparatus for y, that's 1200 equals x squared plus 4xy. I'll start by subtracting x squared from both sides. And then I would divide both sides by 4x. So I get 1200 minus x squared all over 4x is equal to y. Yeah, just to be clear, if the top wasn't open, this would be 2x squared plus 4xy. We would still have the 4xy, but instead of 1x squared here, we would have two of them, one for the bottom, one for the top. All right, now that we have solved the constraint for y, what do?
Solve for x.
Not gonna
You
solve
can
for-
simplify and then take the derivative.
Simplify what?
Can't you like make it 300 over x minus x over 4?
I could, but so this is kind of what I'm trying to get at. What's the thing I'm trying to maximize? Is it this? Or is it something else? Why did I solve this for y?
So you can plug it into the volume equation.
Yeah, my goal is to maximize the volume. And the problem is this volume has x's and y's in it. So in order to fix that, I'd solved this for y. Now I can plug that in here, and that will give me a volume function that I know how to differentiate. So now I plug y equals 1200 minus x squared over 4x in for y in the volume equation. So my goal is to get this volume equation to have only the one variable x in it. And that way I can find the min and max, or whatever it is I'm looking for. So my volume is x squared times y. That is now x squared times 1200 minus x squared over 4x. And the way I would do this is to pop the 4x out. So this is x squared over 4x times 1200 minus x squared. Then you can cancel here. This is x over 4 times 1200 minus x squared. And then I can distribute the x over 4. So I'll get volume V is equal to x over 4 times 1200. That's 300x minus x squared times x over 4. That's minus x cubed over 4. And I like to rewrite this in function notation. Now that I have a function of a single variable, I can say, okay, v of x, and maybe put the dominant term out front. Negative x cubed over 4 plus 300x. So now I have my volume as a function of x. Previously, it was a function of both x and y, and that was an issue. Is everybody comfy up to this step?
How did you pop the 4x over to x squared?
So that piece is down here, right?
Yeah.
That's the same as having this whole thing multiplied by 1 over 4x. So just using some algebra rules here. So what do we have here? We've got something like A times B over C. This is the same as A times B times 1 over C. Because B over C is the same as B over 1 times 1 over C. So I can shuffle that around however I want. And I chose to write it as like A over C times B. That's the sort of algebra rule I was using there.
So could we have still solved it without you doing that or no?
Yeah, sure, you could. Yeah. But it's just the nicest, as to me, that appeared to be the fastest way to simplify it. That's all.
Okay.
But as long as you take this thing and you simplify it, you will get this thing. I definitely don't want to have this x down here if I can avoid it, because I don't want to have to use the quotient rule. And I don't want to have this product here if I can avoid it, because I don't want to have to use the product rule. So kind of just multiply everything out and simplify, however you want to do that. All right. So the volume v of x is the thing I want to maximize. So I should take its derivative. So now I'm going to differentiate v of x and find the max. V primed of x, the derivative, is the derivative of this thing. That's negative 3x squared over 4. Remember, this 4 is a constant, so we don't need to use any quotient rule there. Plus 300. So v primed of x is equal to 0 if and only if negative 3x squared over 4 plus 300 is equal to 0. Which is the same as saying 300 is equal to 3x squared over 4. I differentiated. I took the derivative. So the derivative of 300x is just 300. And the derivative of x cubed is 3x squared. So the negative and the 1/4 came along for the ride. The 300 came along for the ride. But yeah, here we've taken the derivative. So now I'm setting that derivative equal to 0, which means I'm setting this expression equal to 0. And then I'm going to add this term over to the other side. So I'll have 300 equals the positive version of this term. Now I'll multiply both sides by 4. 300 times 4 is 1200. So 1200 equals 3x squared. I'll divide both sides by 3. That'll give me 400 equals x squared. And then I'll take square roots. So plus and minus 20 are equal to x. And then from here I'll say, since x is a side length, I'm only interested in the positive value, x equals 20. Right, I'm not interested in trying to build a box whose side length is negative 20 centimeters. The universe might implode. That would be scary. So my critical number is 20. And in order to verify that this is really an absolute max, I need to make the number line for v prime. So I'll put my critical number on here. I'm going to mark 0 over here just because I know I'm not interested in anything to the left of 0. So I've got the following regions. And in here I can test something like x equals 1. V primed of 1, if you plug 1 in here, this is 300 minus 3/4, which would be 299.25. which is definitely positive. So my V function is increasing everywhere to the left of 20. And on the other side, I could test something like 21. So 21 squared is what, 4? I'm not sure off the top of my head. We're going to use a calculator here if we want, just to double check our arithmetic. Thank you, Trevor. So I'll need to be plugging 21 in here. So this would be negative. Turn on. Cancel. Clear. Negative 21 squared divided by 4. And to that, I'm going to add 300, really? Negative. Oh, I left off the 3. Sorry, so I need to multiply this by 3. Yeah, and then add 300. So we get negative 30.75. V primed of 21 equals negative 30.75. In particular, it's negative. So my volume function is decreasing everywhere to the right of 20.
Can't we just plug in 20 for the original equation and see if it's a min or a max instead of, and then you'll know what side's increasing and decreasing?
Well, how would you know whether it's a min or a max from plugging it into the original? If you plug it into the original, it's just going to tell you the volume of the box with side length 20. But it won't tell you anything about whether you're increasing or decreasing. All the increasing, decreasing information comes from the derivative.
Oh, okay.
If you want to graph the original, you could do that. But remember, you guys don't have graphing calculators on the exams. So I would hesitate to do that. I could set my x-min to 0, my x-max to something like 50. And what is this? Is going to be quite large, right? I'll set this to like, start at 500. And then I could graph the original function here if I wanted to and try to verify that I do have a max at 20. So if I graph this bad boy, oh, still nowhere near high enough on my. Is that U? No, 5. Let's see if this is getting closer. Yeah, so, and we can then kind of try to verify that our absolute max really is right here at 20, and it is. But remember, you guys won't have graphing calculators on the test. So really the only way to check that you've got a max or a min is with our derivative test. If you wanted to, an alternative to using the first derivative test would be to use the second derivative test to verify that this is a local max, and then pray that that local max is also absolute. But really the only way the quickest way to verify that this is the absolute max is this. So then by the theorem we discussed on Monday, since we're increasing everywhere to the left and decreasing everywhere to the right, this has to be an absolute max. And now, depending on what the question was asking, so Joe, if you plug 19 and 21 into the original function, you would notice in this particular case that the volume at 20 is larger than it is at 19 or 21, but that doesn't mean it's the absolute max. That hints at it being a local max. But there's lots of functions where you could have a local max at 20 and have an absolute max somewhere else. And it's also possible to have this not come out, not verify. Like there are plenty of functions. How can I do this? It's not going to happen here, but you can imagine that maybe we have a local max at 20 and then maybe 19 is up here and you have another max there and you've just got some weird behavior like this. And then maybe you've got another max over here at 21. So in theory, it's possible to have graphs that look like this, where this is at x equals 19, this is at x equals 20, and this is at x equals 21. So you could have found a local max and find that these two have higher y values. There's all sorts of weird shit that can happen here. So really you could have something like this going on, and maybe 19 and 21 are here and 20 is here. So you end up at the same height. There's all sorts of funky shit that we could hypothetically run into. And the nice thing is that this actually always works. This will get you out of any situations like this or any situations like this. Whereas like just kind of what you're talking about is sort of a brute force method, where you're finding the max just by comparing the function's value at the point you think is the max to the function's value at some other points. And that's not really rigorous. It's kind of what a computer would do. But if you wanted to make sure that x equals 20 was the absolute max, you would need to plug every real number, not just every whole number. You would need to plug every real number into the original function. And fuck that noise, there's infinitely many real numbers. There's infinitely many real numbers between 19 and 20. I would die long before completing even a fraction of the amount of work that's needed to verify it that way. So this is not difficult, and it really is the best way to proceed here.
So for this problem, there's no local max or min?
Well, this
Or-
absolute max is also a local max,
Okay,
but there are no minima. Yeah. If you restrict the domain to 0 to some other finite number up here, you would have an absolute min and an absolute max. But yeah, no, here we just have an absolute max. It happens to also be a local max, and it occurs when x is 20.
okay. And then I just kind of get confused with like the local max and min. So how do you know it's also a local max too?
Well, remember the
Like-
definition of a local max. If you go from increasing to decreasing at a number, that is automatically a local max.
Okay,
A local max is any hill, right? And this is certainly the top of a hill. So it's the top of any hill is a local max. And the idea is that this local max is also absolute, because in addition to being the top of a hill, it's also the tallest y value on the graph.
okay, thank you. Yeah, that makes sense now.
Does that make sense? All right. So I have an absolute max when x is equal to 20. What did the problem ask me to find?
The max volume.
Right. So how do I find the max volume?
Plug in 20.
Good. And V of 20, where was that? Where was my start? So my volume equation, there's a couple catches here. There's a few ways you can think of this. If you want to go back to the very original volume equation, the x squared times y, you would need to find y. But if I want to be lazy, remember, I've actually already expressed the volume strictly as a function of x. So I could also plug it into this version, and that saves me having to find y. So I'd say V of 20 is negative 20 cubed over 4 plus 300 times 20. 20 cubed is 8,000, right? 20 times 20 is 400. 400 times 20 is 8,000. So this is negative 8,000 over 4 plus 300 times 20 is 6,000. 8,000 divided by 4 is 2,000. This is negative 2,000 plus 6,000, which is positive 4,000. And the units here are centimeters cubed. right? This is when x is equal to 20 centimeters. So that's it. The max volume is 4,000 centimeters cubed. If they ask me what dimensions maximize the volume, they're not asking for the max volume there, they're asking for the x and the y. So if they ask for what dimensions maximize the volume, I would just find x and y and tell them that. Those are my answers. But here they ask just straight up, what is the max volume? So we need to figure out what is the volume of the box when x is 20. Questions on this?
So when we find the derivative of the volume function, it's just going to give us the critical numbers every time.
Yep, derivatives give critical numbers. Yep. So
Did we? Oh, sorry.
No, that's okay. Go ahead.
Did we find the y in this problem or?
Nope,
Okay.
never even bothered.
So how would we do that? Like which equation would we, like the very beginning, like the
You
original
would
one?
come back here.
Okay.
You go back to your constraint. So if you wanted to know, like, what are the x and y values that maximize the volume instead of just what is the max volume, you would come back to the constraint and plug in 20 for x and solve for y. Since this is already solved for y here, I would probably do it here.
Okay, so if it was asking for the dimensions, we would solve the equation for the constraint, like for y.
Yeah, you
Or-
would plug in the x value that you know maximizes the volume into the thing that relates x and y, which is this, or equivalently plug it into this.
Okay. And then that's where we stop for like if it were asking for dimensions.
Yes.
Okay.
Yep. Yeah, you would say, the base should have length 20 centimeters, and the height should be whatever you get out of this when you plug in.
Okay. Thanks.
All right, these are all really good questions and comments. Any other thoughts on this? Anything else we'd like to look at or talk about? And kind of, I'll hold here for a second. You can screen cap if you want. Here's the top. I'll hold here for about 5, 4, 3, 2. And then the bottom of the first page for about 5, 4, 3, 2. And then the top of the second page, about 5, 4, 3, 2. And then the bottom of the second page. All right. Let me go back here. So I think Joe wants to do a related rates problem. I think there were some other problems requested. As I get through those, then we'll look at some related rates. Trent wants to see 25 on homework 8. Tia wants to see 29 on homework 6. I'm going to do those in order. So Trent's question is going to come first here. Close this thing. Was this homework 8? This was homework 7, wasn't it? Yeah, okay. So let's go back and open homework 8. Homework 2, homework 8, that's it. Yeah, I'll get the video up as soon as I can. All right. So, oh no, 25 on homework 8, right? Yeah, so that's, oh, this is a long one, isn't it? Yeah, okay. We want to sketch the graph of x plus sine x. This is quite a bit of work, so I don't want to run all the way through like a through h, but we're going to sketch y equals x plus sine x. I'm going to do this quick, all right? The domain is all real numbers because x and sine x both have domain all real numbers. The x-intercept is only at x equals 0. If you set this equal to 0, you're going to have a difficult equation to solve. But the only way to get this thing to be 0 is if x is 0. So domain is R, intercepts. There's only one. It's at 0, 0. It's both the x and the y intercept. Symmetry. X and sine X are both odd functions. If you add two odd functions, you get another one. So this is an odd function. So there's origin symmetry. And there's no asymptotes. All right, no vertical asymptotes because the domain is all real numbers. No horizontal asymptotes because as X goes to infinity, this piece gets bigger and bigger, and this piece just oscillates between -1 and 1. So that's all the algebra stuff done. Y primed, if we're looking for mins, maxes, and increasing, decreasing, Y primed is 1 plus cos X. So our critical numbers come from 1 plus cos X equals 0, which is equivalent to saying cos X equals -1. So where is cos X equal to -1? Pi, good. Where else? -pi, and also plus and minus 3 pi, and also plus and minus 5 pi. So we got to remember how to solve trig equations like this. The solution, the full solution here is n pi, where n is any integer. So if I start making a number line, maybe I would put like, not any integer, I'm so sorry, odd integer. So x equals plus and minus 2n plus 1 times pi. So I might call this like -3 pi, -pi, pi, and 3 pi just to get us started. So cos is equal to -1 anytime the inside of cosine is an odd multiple of pi. So kind of just to get us started in here, we can use these. Well, there's infinitely many solutions. All right. If you test like 0 in here, then y prime at 0 is 1 plus the cos of 0. The cos of 0 is 1, so that's 2, which is positive. Between pi and 3 pi, I could test x equals 2 pi. Y prime of 2 pi is 1 plus the cos of 2 pi. The cos of 2 pi is also 1, so this is also 2. This is positive. Over here, we could test x equals 4 pi. Y primed of 4 pi is 1 plus the cos of 4 pi. The cos of 4 pi is also 1. So this is 2. You're seeing a pattern, right? There's always an even multiple of pi between any two odd multiples of pi. So you can always test the even multiple of pi. Cosine evaluated at any even multiple of pi is going to be 1. So y prime everywhere in here is positive. This function always increasing. Or at least it's never decreasing. But this is not a min or a max because we're increasing, increasing. We're not increasing, decreasing, we're increasing, increasing. So kind of what's going on here is that we've got these horizontal tangent lines. But they're not mins or maxes. We've seen this happen before with like the function y equals x cubed. He has a horizontal tangent line at 0, but does not have a min or a max there. So it's the same sort of thing going on here. No mins or maxes, we're increasing everywhere, but we have horizontal tangent lines at odd multiples of pi. Y double primed. If I differentiate this again, so now I'm going after inflection points in concavity info. The derivative of 1 is 0. The derivative of cos x is negative sine x. So y double primed is equal to 0 if and only if negative sine of x is equal to 0. And this happens where? What are all the solutions to negative sine x equals 0? The same as just saying sine x equals 0, right? So where is the sine function equal to 0?
0 and pi.
0, pi, where else?
Two pi.
Yeah. 3 pi. And the positive or negative versions of these. So here the solution is x equals plus and minus n pi. All right, any multiple of pi. Sine is 0 at any multiple of pi. So the number line here for y double prime, I'm just going to put a few of these on here, like negative 2 pi, negative pi. Oh, shit, 0 needs to go on here too, right? Yeah, 0. Pi, 2 pi, and so on. So this is going to get a little bit busy, a little bit cluttered. But we can start working like this. Say between 0 and pi, I could in here test x equals pi over 2. So if you plug in pi over 2 to this, y double primed at pi over 2 is what? Well, it's the negative of the sine of pi over 2. What is the sine of pi over 2? Good, so this is negative 1. So we're negative, we're concave down in here. And what about over here? I could test x equals negative pi over 2 between negative pi and 0. What is y double prime of negative pi over 2? If you plug negative pi over 2 in here, the sine of negative pi over 2 is what? It's negative 1. So if I rotate down negative pi over 2, that lands me here. And the y value there is negative 1. So this would be negative 1, which would make this positive 1 overall. So we're concave up here. And then this pattern is going to repeat. Between pi and 2 pi, I could test 3 pi over 2. The sine of 3 pi over 2 is negative 1. The negative of that is positive. So this pattern is going to continue like this. All right, now we're almost out of time. So I'm going to do my best to sketch you a nice graph. This means we're concave up, concave down, and so on. All right. So the shape of F, I'm not going to do the whole mess here. We're just going to do a little bit. I'm going to put 0 here, pi here, 2 pi here, negative pi here, negative 2 pi here. And I'm just going to look from like negative 2 pi to positive 2 pi. from negative 2 pi to negative pi. That means on this first number line, between here and here, right, we're increasing everywhere. In fact, we can just say it, where f is increasing, 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 right? The f prime line is always positive. And then from negative 2 pi to negative pi, we're increasing concave down. And then from negative pi to 0, we're increasing concave up. And then from 0 to pi, we're increasing concave down. And from pi to 2 pi, we're back to concave up. So increasing concave down looks like this. Increasing concave up looks like this. Increasing concave down looks like this. Increasing concave up looks like this. So if I want to draw the graph, I know I have to start at the origin, 0, 0. And I am going to start out increasing concave down. So I'm going to have some piece that looks like this. I have an inflection point here. And if I want to find the y value of that inflection point, I would do that by plugging pi into the original. So that's pi plus the sine of pi, which is just pi. So this is pi comma pi. And then we're increasing concave up. All right, and that's just from 0 to 2 pi. This point over here, this would be 2 pi comma 2 pi. And if I do the same thing over here, I know from negative pi to 0, I'm increasing concave up, so I'm marking negative pi over here. What's this? Increasing concave up. So we're looking something like this. And this would be negative pi comma negative pi. It's going to be an IP. And then over here, we're increasing concave down. It's going to look like this. And we are out of time. We're actually more than out of time. But this is actually a really good picture of this graph. If you want to compare this to what we get in Desmos. Yeah, no problem. I actually really like this function. I'm a big fan. Let's zoom out a little bit. Let's see how far off we are. Not too bad, right? Not too bad. So really, we're just looking at like this part of it, just from like from negative 2 pi, which is like here, to positive 2 pi. I'm a little bit too steep in here. We shouldn't have a vertical tangent. It just should be like this. But yeah, this is good. This is really good. All right. I went through this morning and I started uploading all the videos that I hadn't uploaded yet. So yeah, Holly, those will be up very soon. I do have to run now because I have another class that's starting in literally 1 minute. I gotta go. But I hope this was helpful for you guys. If there are other questions that you wanted to see but we didn't get time to, send me a Canvas message, send me an email, come by an office hour, something like that, and I'll work those out for you. Take care, guys.